Hello, this is Polarized Light Microscopy in Archaeology, and this is lecture 2, which is about everything, everything, and it's essentially the entire first term in a single lecture, of course, which will be elaborated upon in greater length during the term, to give you a head start for the beginnings of the labs, which will be happening relatively soon. And so it's necessary to have a vague idea of what's going on so you understand what's going on in the labs. Now, of course, you know by now that polarized light microscopy means taking a sample, in this case from a piece of pottery, grinding one side until it is optically flat, and then grinding it down on a glass slide to 0.03 millimeters thick. This makes a thin section. This thin section is then put on a polarized light microscope. Light is propagated from the source here. This is a very old microscope, but it shows these things more clearly. And then there is a polarizer. So the polarized light makes the light vibrate in one direction, but then the light goes through the sample and then through another polarizer. So the light goes all the way through, and then you can see what's going on. So in order to see what's going on when both polarizers are on, the upper polarizer can be taken in and out. When it's in, it's called cross-polarized light, and when you take it out, it's plain polarized light. When they're both in, you shouldn't see anything unless the light is refracted by crystals in the sample. Other textures can refract light, but crystals are the most useful thing. So to understand what we're looking at, you have to start off with elements, because elements are the building block of just about everything. A basic chemical substance that cannot be divided into a simpler substance by any means. And I'm sure you all know the table of elements, which includes many elements we'll be interested in. Here are some of them, and the ones that we'll be interested in will be the ones which have high numbers. Oxygen. You may think, well, oxygen isn't very big in rocks and minerals. Well, actually it is, especially found with silica. Silicon quartz is SiO2, so silicon and oxygen, and other common elements are iron in the Earth's crust. This is how much is in the Earth's crust. Iron is quite important. Calcium, potassium, aluminium, manganese, sodium. Yeah, those. And so those are what make up most of the rock-forming minerals. And some of them have funny things that hopefully you'll know what the hell's going on there. So that brings me to what is a mineral? So a mineral, the classic definition, is a single crystalline phase in inorganic nature. So this is just the sort of thing that would be good for an exam question. What is a mineral? And you will say, a single crystalline phase in organic nature. But what does that mean? Well, a single phase is something that cannot be broken down mechanically into its components. For instance, this is the mineral halite, known as salt, sodium chloride. And if you take a big chunk of halite and grind it, all you will get out of it is more halite. So that's what it's meant. It's one phase. It's the same thing all the way through. And you can't break it down mechanically. You could dissolve it into different elements, but you can't break it down mechanically into anything other than a smaller bit of itself. And what is a crystalline phase? Well, I'm sure you've all been made aware of the states of matter, but this is not a gas, this is not a liquid, and this is not a solid. You're taught in school that these are the common states of matter, but in fact there's two others. There's glass, which is actually a supercooled liquid, and so it's actually a lot less moving around than liquid is. And also there are crystals. So a crystalline state is one in which all atoms are bound into a rigid network extending in 3 dimensions. So the 3 dimensions is very important for the next bit, because as you can imagine, these elements in this rigid network go off in the 3 directions. And it's inorganic. There are things that are a bit like minerals which come from organic environments, but typically they come from inorganic, so not organic. And it's in nature. There are some synthetic materials which are also like minerals, but they're not. So it's out there in nature, being wild and free. So, bonding. Various forms of attraction exist between the atoms to form the crystal structure. The most important in mineralogy is ionic bonding, in which you have an ion containing alternating cations and anions. Cations have lost electrons and so are positively charged. Anions have gained electrons and are negatively charged. Electrostatic attraction keeps these atoms together. So, for instance, as I mentioned previously, sodium chloride, also known as halite and also known as salt. So you have chlorine and sodium, making sodium chloride. Cation is sodium, and the anion is chlorine. So this is where I'm going to show you an aid to memory that, if you look very hard at the screen, will go into your brain and help you remember the order of this for the rest of your days. So look very carefully in the bottom left-hand corner of the screen and absorb what you see. There's the cat on the left and the onion on the right. Okay, just the cat is on the left and the anion is on the right. So just like the cat ion is on the left and the anion is on the right. So that's why we will call this a sodium chloride. It's not a chloriated sodium-y thing. It's sodium chloride because what? Because the cat is on the left and the anion is on the right. So always remember this. So sometimes the anion may be an anionic group kept together by covalent bonds. It means their valency is the same and they like each other. One of these is calcite, which is a very important mineral in the carbonate group. We will get to know calcite very well. So this is calcium and carbonate together. Gypsum is a sulfate with sulfur and oxygen together. It's also got water in it. A lot of minerals will have stray bits of water in them. Well, they're not stray; they're rigidly in the structure of the mineral. But the fact they have water in them is very important. So these are both covalent bonds creating anionic groups, and quite often we will call them carbonates or sulfates rather than be specific about the mineral type. At other times, the cation may form a solid solution series, like the pyroxene group. Now here on this exciting graphic, you can see we have different minerals. These are different minerals. Enstatite, ferrosilite, diopside, augite, pigeonite, hedenbergite, and wollastonite. And these are all very closely related minerals. They're all like in a continuum. And the ones down here have magnesium and silicon oxygen, so it's a magnesium silicate. One over here is iron, a ferrous silicate. And in between, there's a mixture of the two. Up here in this extreme is wollastonite, which is a calcium silicate. And you have all these other minerals which are in between. Like augite here, or augite, is sort of halfway in between the three. So this would be a calcium, magnesium, iron silicate. Sometimes, and this is a bit more complicated, aluminium, it also gets in, because aluminium works up covalency very well. So often you will have aluminosilicates. Aluminosilicates are very important in pottery because that's what clay is. And we don't see clay in thin section, so we will be talking about it a lot, but it's, of course, quite important. So, those 3 dimensions I was talking to you about, in which crystals extend, are very important in crystallography. So a crystal is an ordered atomic structure forming a 3-dimensional network. Remember, 3-dimensional network. So, as you can imagine, each of these dimensions have dimensions. Now, the simplest one is each of the dimensions are equal. In each of the 3 directions, they are equal. And this is the isometric or cubic system. Then you have the tetragonal system, the orthorhombic system, the hexagonal or trigonal system, the monoclinic system, and the triclinic system. And I'm going to go through each one of these, so don't panic about them yet. So the isometric or cubic system, it's called the cubic system because it makes cubes a lot. So this has these 3 axes, and they're all at equal length, and they're all at right angles to each other. So from this, you will logically work out what the rest are about, because quite obviously the others will differ from this in having different lengths and different angles, but we'll go through them anyway. It doesn't just form cubes, it forms all sorts of weird things. The tetragonal system is the next one. So as you can imagine, you have 2 axes which are the same, and one which is longer. And what we will do is say the one which is longer than the other 2, we shall call the c-axis. Axis, not the axes, the axis. And so the c-axis is probably the one thing I will want you to take away from this, because it can be very important. Sometimes it can be longer, sometimes it can be shorter, sometimes it can be exactly the same length. Now, one of the distinctions of the previous system, the isometric system, is that it is isotropic. Light is propagated equally in all directions. And so it's just like glass. When you're looking in cross-polarized light down a microscope, you don't see anything because light is blocked. And so there will come a time when you are looking at a mineral in the lab and light is not passing through it in cross-polarized light, but it's clearly colorless and clear in plain polarized light, you will be saying, I have found a garnet, which is a more common isometric system mineral. And either I or Professor Sunahara will come over and say, no, that isn't. You're looking down at another mineral down the c-axis. Because you imagine, if this is a mineral with the shape of a mineral, it'll be longer in this way, and it may be oriented in the thin section so that what you're doing is looking down the c-axis. And so in that direction, this looks like it would be isometric, but it's not. So that's why it's worth knowing this one axis. Forget all the rest. It's the c-axis that you'll need to know when somebody's telling you, no, it's not isometric, you're looking down the c-axis. And as you can see, it can be shorter, and it forms crystals that are shaped like this or like that. The orthorhombic system is the next logical thing. Each axis is any old length, although the angle between them is at 90 degrees. The hexagonal or trigonal system is a bit of a fly in the ointment because it has all sorts of other axes. So it has, again, a c-axis. So this, again, is an important problem for people finding garnet when they're actually looking at minerals like quartz, because this is the crystal system of quartz. So if you have ever gone weird when you were at high school and got quartz crystals, not that that's weird, I won't want to be pejorative, I believe in quartz crystals, go straight ahead. And these are, if you've seen quartz crystals, exactly what you're dealing with. These 6 sides created by this crystal structure and a long crystal going in this direction. And the monoclinic system is back to just 3 axes, and they're all any length, including the same length, and one is at an angle, which again could be any angle, including 90 degrees, because that's just annoying. Typically it's not, though. And then, of course, you have the triclinic system, which means all bets are off. Everything can be any length, any angle could be any angle, including 90 degrees, and they can all actually be the same length, just to annoy people. So that's a précis of the 6 systems. So as you can see, this is sort of shape they can form. You'll be able to use this quite often to identify things. Isometric things will be quite obvious, unless of course you're looking down the c-axis. And when we get to extinction, which is not about dinosaurs, but about when you rotate the stage of a microscope, which is an important aspect of a polarized light microscope, you will at some time align the crystal so that it is parallel to the direction of the polarized filters, and it will disappear. And in that case, it's a matter of, does it disappear, extinguish, go extinct, parallel to the crosshairs down the microscope? Imagine there'd be like these crosshairs in the microscope. Or does it extinguish at an angle? And so that, again, is a very important distinction between different types of minerals. So crystal habit is important. It's really important to sort of understand minerals, but it's mostly important for description, because the most important thing to do is to describe what you're seeing. It's more important to describe it than to actually identify a mineral, because if you identify a mineral and you're wrong, then you have identified a mineral wrong. But if you have described it, then other people can say, oh, I think they found this, even if you can't identify it. So it's actually very useless, far too better to describe it than to identify it. Although it's actually better to identify it correctly, of course. So these shapes, these habits include euhedral. That means it's crystal shaped, dictated by the internal structure of the mineral, like these are. You see, these are dictated by the internal shape of the mineral. Equant, 3 dimensions are the same, or actually 2 when you got it cut through it. And of course these are equant. So you can say that about them. Prismatic, 2 dimensions are equal. One is very, very long, forming a prism-like thing. Acicular, which is needle-like. 2 dimensions are similar. The third is much longer. These are acicular, and you may get acicular inclusions in your thin section. And tabular, which means it's table-like. 2 dimensions are similar, one is much shorter. Micaceous. It means it's like a mica, which means it's a type of mineral which you'll get to know better. Biotite and muscovite are the common micas, and they grow crystals which aren't actually micaceous. They're like blocky crystals, but they have this thing called cleavage. More on cleavage later. And they break very easily into very thin sheets. And so they'll have 2 dimensions which are similar and one which is very, very short indeed. Cleavage. I said I was going to mention cleavage. So, cleavage is a innate weakness in the atomic structure and forms what at first view looks like cracks in a mineral. This is a type of mineral known as hornblende, which is in a group of minerals known as amphiboles. And all of the amphiboles have these 2 cleavages. You can see they're at 120 degrees, always at 120 degrees or so. You can see here. And when you see this a line going across a mineral, it's very probably a cleavage. It might not be. But one thing you want to look out for is parallel lines. So then you know that this structure goes all the way across the mineral. And here, of course, you can see other ones going this way. So if I saw this, I could quickly say, oh, that's an amphibole of some sort. And then I'd want to figure out which type of amphibole it is, if I can. Quite often, it might be better just to say, this is from the amphibole group. And so they have descriptions. Most of these, like fair and poor, you probably wouldn't even see in a thin section. These terms are used more often for a hand specimen mineral you're trying to identify. But as you can see, this is a nice, clearly defined cleavage, which you will recognize quite easily. So twinning. So this is a body formed as a result of 2 or more crystals of the same species governed by crystallographic law, so that one is related to another by rotation axis or mirror plane. Now that is a lot of guff which you don't need to remember. You just need to remember that twinning is what forms very interesting patterns that help you to identify minerals. This is the potassic feldspar microcline, and this is what it looks like in plain polarized light, which is a very uninteresting mineral that looks very much like a whole lot of other minerals, especially other feldspars. But in cross polarized light you can see the twinning. This is called tartan twinning because it goes one way and the other. And so what twinning does is create these crazy patterns that are really wonderful for helping you to identify that this is in fact microcline. It's the only mineral that has this type of twinning, and it makes it very easy to distinguish between the other feldspar, plagioclase. Plagioclase always has what is known as lamellar twinning, blade-like twinning. And so when you see these very straight lines like a zebra, you're looking at plagioclase. Very easy. So mineral classifications. This is how we order minerals. Common method of classification that geologists use and love, and mineralogists, all those crazy earth-loving people. So this groups minerals together by their anions. Remember, the anions are on the right. And I'm going to go through each of these, but they are native elements, sulfides, sulfur salts, oxides, halides, oxy-salts, carbonates, silicon, silicates. And some of these are not going to be brought up again. The native elements, for instance, can be theoretically of one element, divided into metallics like gold and silver, and then non-metallics like diamonds and sulfur. And of course, we don't get a lot of these in the thin section, so don't worry about it. Not important in pottery, yeah, that's what I just said. Then there are the sulfides, like arsenides and tellurides and things like this, which are very important ore minerals. But things like galena, pyrite, nickelite, very important, but not important in pottery. The sulfur salts are so important I couldn't even be bothered to find an example. Oxides, again, very important ore minerals. But things like oxides, like hematite, magnetite, iron oxides, and the sulfides, in a thin section, and we're just doing transmitted light. We don't do reflected light because we don't do that. But in transmitted light, all of these minerals are just opaque. And so you'll just be saying, this is an opaque. Under plain polarized light, under cross-polarized light, all you see is blackness. So the halides, again, are very important. Salt is a halide, but you don't get them in thin sections, so don't worry about them. The oxy-salts, including carbonates, are very important rock-forming minerals. You will get to know calcite very well. It will become your friend. Calcium carbonate. Dolomite is the calcium-magnesium carbonate. These are very difficult to tell the difference between them in thin section. And so what you will be encouraged to do is just say, there's a carbonate in my thin section. And it's better to call it carbonate. Sometimes you might be able to say, oh, this is actually calcite, or oh, this is actually dolomite. But that's quite rare. And I'll be telling you how that happens in another lecture. The sulfates include gypsum. Very important mineral. You can make plaster out of it. It's what is often called Baghdad marble or alabaster, and you can make buildings out of it. But you don't see it in thin section. Not typically, anyway. The phosphates, however, you do see it. Apatite is an important phosphate. PO. Phosphorus and oxygen. Fluorapatite is the crystal that grows in your bones, in all bones actually, and so fluorapatite will often be in the bones of dead animals that die in the sea. And I'm sure you know that flint and chert are the skeletons of sponges which have sunk to the bottom of the sea. A lot of limestone is made of shelly organisms that die and their shells sink to the bottom of the sea. And also when bony organisms die, that leaves a residue of phosphate. And so you get these rocks, phosphatic rocks or phosphatoids. And we do get those, especially in Jordan. So if you're looking at a thin section of a piece of pottery from Jordan, there's a good chance you will see phosphate in it. So we will cover that. And then we come, of course, to silica. And there's the quartz crystal. You feel the vibrations. So primary variants of quartz. And you get macrocrystalline and cryptocrystalline varieties. This is the macrocrystalline. The cryptocrystalline will include chalcedony and chert and flint, things like that. And this is a very important rock forming mineral, and we see it every damn where. And then we have the silicates, which is any mineral with silica other than silica. So these are a very important group of rock forming minerals, such as the feldspars. This is a feldspar. Notice the cleavage. See, isn't that nice cleavage there? So optics, moving right along. Optics are very important. This is about light. So, what is light? Well, let me tell you. Light is a transverse wave motion consisting of rapidly alternating electrical and magnetic disturbances which vibrate in all planes, including the direction of advance of the disturbance. So here's light being propagated, here's light being perceived, and all along the direction of the advance of the disturbance, it is vibrating. You can see it's vibrating here in this dimension, but it's actually vibrating all the way around. It vibrates in every dimension. And it has things like a wavelength, and it has an amplitude. All these are measurable attributes. So a light ray, which is what this is a line from the source to the point where the light is perceived. The light velocity is the distance traveled by the crest, this is a crest, in time. So light will have a velocity. the frequency of the vibration is the velocity divided by the wavelength. So you're looking at all this and thinking, oh my God, what? Okay, well, one important thing to get from this is that it's vibrating every direction, of course, and we already know that. And we know that a polarized filter will block that, so it's vibrating in one direction. And you take another polarized filter and look at it at right angles to the other one, then you won't see anything at all. So this is where we get into certain aspects of this. Polarized light vibrates in a single plane, like this. So that's light vibrating in every direction, goes through the polarizer, vibrates in one plane. So isotropic material, the velocity of light is equal in all directions of propagation. So that includes things with no structure, like a glass. So glass, like anthropogenic glass, like the glass you drink water out of, will not propagate light differently in any direction. Volcanic glass that you might see in a thin section in a piece of pottery, well, also light is propagated equally. So it's isotropic. Under cross-polarized light, there'll be nothing to see. Just nothing there. And so also the isometric system is isotropic because light is propagated equally in all directions because of the length of the axes. So what happens when you have different length of axes is you get anisotropic material. And so light will travel at different velocities in different directions within the material. And so that is what causes refraction. So if there is an anisotropic material in here, it will create refraction, and then there will be light. Light will dawn upon your thin section, and you will see clearly that there is light. And even when there's a polarizer, and it's cross-polarized light, you will still see that there is some light. It won't be completely blocked, because the light has been refracted. So the refractive index is very important. So this is what it actually means. When light passes from one substance to another, it is either speeded up or slowed down due to the difference in atomic structure. So the Ri, refractive index, is equal to the wave velocity in a vacuum divided by the wave velocity in that substance. So that's a refractive index. Everything has a refractive index. You have a refractive index, I have a refractive index, but what we care about is minerals have refractive indices. And what this leads to is what we call birefringence. And that's what all this is at the bottom of the screen, each way along. This is refraction caused by this birefringence, which is the difference between the different axes and their lengths. So that's a measure of the double refraction in anisotropic materials. So the birefringence is the highest refractive index minus the lowest refractive index. So you don't really need to know what a refractive index is, you just need to know where does that put your mineral on this spectrum. And this is actually not a spectrum, it's several spectra. As you can see, this looks like a spectrum. It looks like a slightly more washed out spectrum. This is an even more washed out spectrum. And basically, the higher the order, the closer you get to white light. So when you have minerals with a refractive index, which can then give you their birefringence, this is the thickness of the thin section. This is very important. See, thickness of thin section in millimeters, 0.03. Quartz. The birefringence is about 0.009. It's not a lot. That's here. And so in a thin section, it's this color. So it could be like white or washed out yellow, but it's always about here. Okay? So that means you don't see any of these crazy lights when you're looking at quartz. Biotite, however, the mica, has some crazy stuff going on. So you can see its birefringence goes from 0.03 up to 0.07. And so you can get all these crazy colors in a thin section of biotite when you have cross-polarized light. here we have a thin section in plain polarized light. This is the biotite, and you can see this is the cross-polarized version. So here is a feldspar, and here is quartz, and you can see those are first-order gray. Okay, first-order gray. Their birefringence is so low, it's like right at the bottom here. I'll go back. It's right at the bottom here. So this isn't white light. This is first-order gray. Okay, it's very, very different. White light is all the way up here somewhere. Keep going. See, just keep going off the thing. It's way off here somewhere. So this is first-order gray. So polarized light effects, this is plain polarized light, include absorption, which is that wavelengths of light are absorbed by crystal. What that means is it has a color. And what's interesting about that is when you're looking at it in plain polarized light, and then you rotate the stage, it changes color. That's called pleochroism. So this doesn't happen to all minerals, but it basically, because you're looking at plain polarized light, you're actually only looking at light vibrating in one direction when it goes through. So at different times, when the crystal is in different orientation, then its absorption of the light is different. And so the colors will change. This is called pleochroism. And so minerals which are pleochroic are very distinctive and easily identified, like biotite. Extinction is very important. I mentioned extinction. Remember I mentioned extinction? Basically, okay, if you assume this isn't actually plain polarized light and cross-polarized light, but just think this is what quartz looks like when it's in extinction. Light is not passing through it. If you rotate the stage so that the orientation of the polars is not at right angles to the orientation of the crystal, then it will look like this. So that's that extinction. You get this thing called undulatory extinction, which is quite important, which you only get in quartz. And this means that when you go from extinction to not extinction, that it sort of washes across it. Other minerals will just go extinct, not extinct, blink, blink. Whereas quartz will quite often, if it's got this undulose extinction, the extinction will wash across the inclusion. There is parallel extinction. So this will be parallel to the crystallographic direction. So that means it's a monoclinic or triclinic mineral, and it's not necessarily becoming extinct in the same direction as, say, a cleavage in the mineral, or facet of the crystal, or a twin, if it has a twin in the mineral. Symmetrical. That would mean it extinguishes equally one way and the other way. And inclined. Vibration direction at any angle to cleavage. So this is parallel and inclined. Relief. I think you'll be relieved when we get to the end of the lecture, but relief is actually sort of like a relief map. Now if you look at this, you sort of think, oh, it looks like these minerals are sticking up more from the thin section than the others, but they're not. They have a much larger difference in refractive index between the glue, which is over the thin section, than these do. The minerals here, and you can imagine that this is a whole bunch of other minerals which you can't see, will have a very close refractive index to the glue, the mounting medium. So if you look at this table, this will be in the manual, which you should find available to you. This is the glue. This is the epoxy medium that we use for making the thin sections. And so what happens is the closer it is to this line, then the lower the relief is. So it's not about how high the refractive index is, it's how high it is compared to this. And so it could be very low relief, very low refractive index, and be just as far away from the glue as something with a higher refractive index. And so here we have low refractive index, like the feldspars and quartz and things like that. Down here, calcite and dolomite, and up here we have other minerals like olivine, which we will cover, and garnets, which are high relief. And so these all stick out of the thin section. Calcite and dolomite, the carbonates, are interesting in that they have a very wide range of refractive indices, so a very wide range of relief, because it goes from no relief to quite a moderate amount of relief. This is the only common mineral that does that. So one way you will be able to identify the carbonates is that the relief will be related to the orientation of the mineral in plane polarized light, because, you know, when you rotate the stage, it'll be different. And so when it's oriented to one axis, it may have no relief. But you rotate the stage, and the inclusion becomes at a different orientation to the polars. It may have moderate relief. And so this blinking on and off of relief is almost unique to the carbonate group, and a good way of identifying it. So, minerals, you have opaques, you have isotropic, you have the anisotropic, which is everything else. So we'll be covering minerals, the important minerals one by one, but not yet. So, having done all this, you can look at this horrifying pile of information and actually start to understand what you're looking at. So you'll get all this data, and at the moment you'll say, what on earth is all this rubbish? But what I hope you will gain is to actually start to understand how this can help you. So this is a group of pyroxenes. Remember the pyroxenes? ENSTATITE-ORTHOFERROSILITE. These are orthopyroxenes. That's because they're in the appropriate system, orthogonal system. You can see they have cleavages. We'll get to that in a minute. So there's the magnesium and iron silicate. It's in the orthorhombic system, orthopyroxenes, you see. The refractive index is 1.650 to 1.788, so that tells you this is going to be quite high relief. So you can see it sticks up quite a lot. So yeah, okay, I'm looking for a high relief mineral. This is a high relief mineral. The birefringence, therefore, relation to the glue, is actually not that great. And so it's not, doesn't have all these crazy colors like here. It's usually around here somewhere. This is actually plain polarized light, so you're not going to see them anyway. Cleavage. The cleavage is very important for all the pyroxene group, in that they have two cleavages, and usually I will say it's 90 degrees. Just to be annoying, nature has decided it's actually 88 degrees. But when I say, oh yes, does it have two cleavages at 90 degrees? Yeah, I mean 88, but don't worry about it. If you say it in a test that it has 90 degrees, you will not fail, and you won't get extra marks if you say 88. So you can see the cleavages aren't as good as the amphibole group, but you can see when you see two cracks which are more or less straight and they're parallel, you know you're actually talking about a cleavage. And here you can see that they are sort of at right angles to each other. So that's a pyroxene. The color in plain polarized light, so there you're looking at the absorption. It goes from colorless to reddish or greenish. So this is probably an iron-rich one because it's reddish or greenish, sort of reddish greenish. Pleochroism. The magnesium ones don't have it, but the iron-rich are weak to strong. So in plain polarized light, if you rotated this stage, and it's possible that this is actually the same mineral, only in a different orientation, it will change color when you rotate the stage in plain polarized light. Relief, moderate to high. You already know that because of the refractive index, of course. Distinction is important to, how can I tell the difference with this and other minerals? From the clinopyroxenes by pleochroism, lower birefringence, and straight extinction. That's the only thing you could confuse it with. Occurrence, ultramafic rocks and medium to high grade metamorphic rocks, and possibly in your pottery. So that will bring us to actually rocks, and we will be talking a bit about rocks. But in pottery, any inclusion that contains more than one mineral is a rock, or a lithic inclusion. So here you can see there's this inclusion, and it's got different minerals in it. So this is a rock. And so we'll be classifying rocks as igneous, metamorphic, and sedimentary. This is actually a metamorphic, a sedimentary rock, shale, mostly made of clays and fine silty quartz. So the petrographic description, it's very important because you'll be doing that. You'll want to cover abundance, sortedness, size, roundedness, and, well, that's basically it, really. So this is how we do abundance with these comparison charts, and you should find these in the manual. And this version of it doesn't seem to have it very well, but this is like 1%, 2%, 3%, 15, 20, 25. This is like, there are some missing in the middle. And so basically what you do is you look down the microscope, you look at the mineral you're trying to create an abundance for, you try and isolate it from all the other ones, and try to see where that works looking at the comparison charts. Does it look like it has 2%? Or does it look like it has 3%? Now, I'll go into greater length of this when we talk about this in the lecture, but there are more precise ways of finding out the abundance, but not necessarily more accurate ways of working out the abundance. The difference between precision and accuracy is precise. It will work out by doing it that it has 2.7 abundance of a mineral. Accuracy means it's actually 2, and you can say it's 2. So it's probably better to be accurate than precise, if you know what I'm saying. So I used to do what is known as point counting when I worked in the geology department at the ROM, in which you count 1,000 grains in a thin section. This was of this granitic rocks up in the Canadian Shield, and so in measuring the abundance of these, you count 1,000 grains and work out the abundance of each one. And so I would do all this point counting, and I would bring the results back to my boss, who was the head of department, and he would check my findings to make sure they were actually right by looking at comparison charts. So it was good to do all that counting and have all that apparently precise scientific data, but he made sure it was right by looking at comparison charts. So it's very rapid, very easy, and it's actually scientific, so do it. And also, this is quite useful. This is actually a graphic I made, and if you read the manual, it shows you how this is related to well-defined parameters defined by sedimentologists. The degree of sortedness of grains is an important way of defining what you're looking at. It often relates to the maturity of sediment. A mature sediment tends to be very well sorted, and an immature sediment tends to be very poorly sorted. So it's quite useful to be able to describe how well sorted, one of these four is the inclusions you're looking at. Grain size, so when you have your description, you will be measuring it, of course, in the microscope, but in the description you will not be saying this was about 0.25 to 0.5. You will say, this is a medium sand, as in the examples provided to you. And roundedness. And there's a slightly better graphic. A lot of roundedness literature is based on sedimentologists looking at isolated grains, particularly when they're looking at drill cores for looking for oil or something. And so you can see these are actually isolated grains. We're looking at slices through grains, and so I've developed more precise definitions of what that means. So you should probably use what I say rather than this graphic, but that's fine for now. So now you are capable of doing all of this. Thankfully for you, the first lab will not have all these minerals, it'll only have two of them. It'll have carbonate and quartz, which you'll easily be able to distinguish, and so you'll be able to concentrate on doing things like sorting and roundedness, grain size, and abundance, which is down here, and also doing a lovely drawing. So that's the first term in a single lecture. I hope you liked it.